that stuff out. A1, right? So what we're going to be looking at here is just simply straight up Le Chatelier's principal problems. And so the easiest way to approach it, right, is to write out the equilibrium expression. And so in this case right here, right, K is going to be equal to the concentration of CO gas, right? So it's a gas, and then the concentration of H2 gas, right? And that's going to be to the power of 3, right, because it has coefficient of 3 right there, divided by the concentration of CH4 times concentration of H2O gas, right? So all of them are gases. H2O is not a liquid in this case. If it was a liquid, it wouldn't be included in the equilibrium expression, right? So this is the easiest way to think about what's going on in these cases and kind of think about all these types of problems, is to first write this out, because you can then easily see, are you removing something from the numerator? Are you removing something from the denominator? Are you adding something to the denominator? Are you adding something to the numerator, right? How is that going to affect everything? And so now, right, all the different scenarios that we've come up with that could affect it, right? So one thing, CO gas is removed from the equilibrium mixture, right? So if we remove CO gas, if we're taking that out, then that means that our numerator now is going to be smaller than what it previously was, right? And so now that means that the K value is going to be below, the Q, right, value is going to be below the K. And so if Q is below the K, then that means that product formation is favored, because you have to generate more product, remove more of the denominator, right? So remove more of the CH4 and H2O to form more of that, reach equilibrium again. And so, by doing that, right, by taking out the CO gas, you're going to start forming more and more product, right? So my laptop died. Or it's about to, at least. Right? Right, so product favor, right? Formation of H2 is gonna be produced more of. Next, right, water vapor is removed, right? So if you remove water vapor from this reaction, so if we take that out, in this case, that means that the denominator now is smaller than what it was before. So if the denominator is smaller, then that means that Q is going to then increase and be higher than K. And so if Q is higher than K, then that means that reactants are going to be favored in that case. So if reactants are favored, that means that we're going to be losing H2, right? We're going to actually start consuming it instead of forming it. And so, we're going to end up with something that's reactant favored in that scenario. Next, right, CH4 gas is removed. Same thing, reactant favored, because again, the equilibrium is going to shift so that you're going to have to, produce more of the reactants to get back to from Q down to K, right? Because Q is going to be larger because the denominator is smaller. D, right, the temperature of the equilibrium mixture is increased. So the next thing to think about, right, is if we're thinking about just simply, right, the expression delta G is equal to negative RT natural log K in that case, right? So if T increases, then that means that delta G becomes even more negative. And so if delta G becomes even more negative in that scenario, right, then that means that it's going to want to make more of the product, right? It's going to want to, push that, reaction forward even further. And so, another way you can think about it too, right, is if we're looking at it, delta H in this case is positive, right? So it's an endothermic reaction. So that means that you have to put energy in to the system, right? You have to put heat into the system for it to actually, progress. And so if you put more heat into the system, right, it's going to want to progress more, right? So in this way, you can kind of, do a whole scenario where you claim like, oh, okay, right, heat is actually a reactant as well, right? Because you require it for that reaction to go, right? So you're going to be forming, more products in that case. And then E, right, the equilibrium mixture is transferred to a larger reaction vessel, right? So if we transfer it to a larger reaction vessel, in this case, what happens is that all of the concentrations are going to go down. And if you remember, right, thinking about what's going on, if all of the concentrations decrease in this case, the biggest thing that's really going to be affected is going to be the H2, right, because it has that power of 3 in that case, right? So you have more molecules of product, right, of gaseous product, right? There's 4 molecules of gaseous product that are formed versus 2 molecules of reactants. And so then that means that there's more space for more of the products to actually, grow into, so to say, right? Be synthesized into. And so, the to go from that new Q back to K, right, you're going to have to form more reaction products in that case for it to shift in that direction. By doing that. Similarly, right, like flip side, if you were to take this reaction and all those same number of molecules and you put it into a smaller vessel, because you have more molecules of product versus more molecules of gas, right, it's going to want to then shift in the other direction, right, because you're going to have more of a partial pressure, more of an effect on that system by addressing it that way. So you get more product for part E as well, right? Excuse me. And so that's all the ones that I'm going to work on today and everything like that. So good luck on the exam, and let me just go post these.